Today we are going to cover counting principles. This requires to uh, understand some formulas such as permutation, combination, and factorial. So the focus is on the three concepts: factorial, permutation, and combination. Okay. So again, we require formulas. There are 5 different methods of counting the number of possible outcomes in a variety of situations. Okay, so not all counting problems can be solved with these 5 methods, but they do provide a strong foundation for the most common real application, right? Multiplication rule, counting rule. So if a sequence of events in which the first event can occur n ways, the second event can occur n, uh, n 2 ways, the third event can occur n 3 ways, and so on, the number of outcomes is n1 times n2 times n3, right? So for instance, if the first event can occur 3 times, 3 ways, the second one 5 ways, the third one 6 ways. So just do 3 times 5 times 6. Uh, multiplication counting rule. When making random guesses for a known 4-digit passcode, each digit can be 0, 1, 1, 0, 1, up to 9. What is the total number of different possible passcodes, given that all the guesses have the same chance of being correct? What is the probability of guessing the correct passcode on the first attempt? Right. Right. So we are making 4-digit passcode, and each digit can be 0 or 1 or 2 or 3 and so on, and up to 9. Right. So what is the total number of different possible passcode? How many different possible passcode can we make? For instance, one passcode can be 1, 2, 3, 4. That's one option. Another one can be 2, 1, 3, 4. Another one can be 0, 1, 2, 3, and so on. But each number in the 4-digit passcode can be 0, can be 1, up to 9, right? So when you count 0, 1 to up to 9, there are 10 digits total, right? So let's see what. There are 10 different possibilities for each digit. So the total number of different possible passcode is n1 times, n2 times, n3 times, n4, which is 10 times 10 times 10 times 10. This means each number can be 0 up to 9. So there are 10 different ways to write each single digit. There are 10 different ways to write n2. There are 10 different ways to write n3, and so on. So 10 times 10 times 10 times 10 is 10,000. Because all of the passcodes are equally likely, the probability of getting the correct passcode on the first attempt. So remember, these are the 10, the different ways, the total number of different ways, possibility to get 4-digit passcode, 10,000 ways. So that means there are 10,000 4-digit passcode that you can create, right? So now you're only getting one correct passcode. Not all of them are correct, only one of them. So the chance of getting the passcode correct will be 1 out of 10,000. Because you have 10,000 ways, so you're picking one, selecting one good one out of that. So the chance is very low, 0.0001. Now we're going to talk about factorial. And the notation of factorial is n factorial. N and exclamation mark n factorial. The number of different arrangement. So here the order matter, when we say order matter, there is first place, second place, third place, and so on. So that's where we use a factorial. We're gonna also talk about permutation, where the order matters, where there is first place, second place, and so on. So the number of different arrangements of n different items when all n of them are selected. So you select all of them. For instance, if you pick 5 students, you have 5 students, and you want to order them, arrange them from first, second, third, fourth, and fifth based on their grade. So there are 5 students and there are 5 slots, right? Because first grade up to from first to the fifth student. So we can use factorial for that because the order matters. So that will be 5 factorial. Then we're going to go over some more examples. So the factorial symbol is this, right? Denote the product of decreasing passive whole numbers. So when we say whole numbers, we are talking about 0, 1, 2, 3, and so on. No decimals, no negative number, all passive number, decreasing. So the numbers going down. For instance, if you say factorial 9, so you start from 9, and then 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? So that's factorial 9. Factorial 10, 10 times 9, 10 times 8, 10 times 7, up to 1. But there is a special case here, 0 factorial. 0 factorial is 1, right? So that's the special case. And, so just keep that in mind. 0 factorial is 1. The factorial rule is based on the principle that the first item may be selected in different ways. The second item may be selected n minus 1 way, and so on, right? So if you select the first one, for instance, your first student, second student, up to fifth student, the first student can be selected 5 ways. So that's why we have 5. The second student can be selected 5 minus 1 way, which is 4. The third student can be selected 5 minus 2 way, which is 3, and so on. A statistics researcher must personally visit the president of Gallup, Nilsson, Harris, Pew, and Zogby polling companies. Now the question is, how many different travel itinerary are possible, right? How many different possible? How many different ways? So how many different routes can he take? Remember, you can start from Gallup, and that could be first. Nilsson can be second. Harris can be third. Pew can be fourth, and so on. Or you can start from Nilsson, and then Gallup second, and Harris third, and so on. So how many different travel routes can you take? If the itinerary is randomly selected, what is the probability that the president are visited in order from youngest to oldest? Right? From youngest to oldest. So remember there's only one way. You cannot be younger and then older at the same time. So there's only one option there. So for those 5 different presidents, the number of different travel itineraries is 5 factorial. 5 times 4 times 3 times 2 times 1, which is 120, right? Because the order matters here. There's first, second, third, fourth, fifth, right? So you must choose a certain order, right? So that would be 120. So what should be the probability here, right? You're only choosing 1 out of 120, okay? So there is only one itinerary with the president visit in order of age. So the probability is 1 out of 20. Now we can talk about permutation. Permutation of items are arranged in which sequences of the same items are counted separately. So this here means order matters. We're talking about the sequence. With different sequence of the same items are counted separately. So for instance, if you have letter ABC, the letter arrangements of ABC, there are different ways. ABC is one way, ACB is another way, BAC is another way, BCA, CAB. and CBA are all counted separately as 6 different permutations, right? Because here the order matter, A is in the first place here, B is in the second place, C is in the third place. Here, A in the first place again, but this time C is in the second and B is in the third. Look at this permutation. B is in the first, A is second, C is third, so and so on. So the order matters here. So there are 6 different permutations. Then when it comes to combination, the order for combinations, the order does not matter as long you have the 3 digits, 3 letters, A, B, C. So ABC, ACB, BAC, BCA, CAB, and CBA are all considered to be the same combination, the same exact combination. The order does not matter for combination, right? For instance, if you have 3 digits, 1, 2, 3, there is no first place, second place, third place. So it's only one combination. But if I'm using permutation, it's the same thing. There will be 6 different permutations, right? 1 can be first, and 2 second, 3 is third. 2 can be first, 1 is second, 3 is third, and so on. So we have 6 different permutations. But if we use combination, we'll have only one single combination. So remember, permutation position, where the alliteration remind us that with permutation, the position of the item makes a difference. So the order makes a difference. The position, the location of the items makes a difference. Combination committee, which remind us that with members of a committee, rearrangement of the same members results the same committee. So order does not count. Order does not matter. You don't count the order. For instance, ABC, CBA, BAC, it's the same thing for combination, but they are different in terms of permutation. Now, the formula for permutation, say when n different items are available and r of them are selected without replacement. So you have n items. For instance, you have 10 students, right? 10 different, so there must be 10 different students. And you are selecting 3 students out of those 10 students. So to be first, second, and third, right? The first 3 students based on the grade. So we call it permutation because the order matters here, right? So that will be 10P3. You have 10 students, you are selecting 3 students out of 10. 10P3. The number of different permutation already count. So 10, and so we NPR is n factorial divided by n minus r factorial. So remember, n is always greater than r, because if you have 10 students, you cannot pick 11 students out of 10. It's not possible. You have you cannot pick 12 students out of 10, right? It has to be either the same or less than the n. So r is either less than the r is always less or equal to n, right? Which means n is always greater or equal to r. All right, so a winning $2 trifecta bet in this race won 3,424.60. But that is not important here. That's not asking. They didn't ask you to find that, so you don't worry about that. Permutation rule. When some items are identical to others. So sometimes you want to arrange some items, but some of them are identical. For instance, I want to arrange letters, the like a word, it's almost like a nonsense word. I have A, 3 letters A. I have 4 letters E, 4 times, and B, 4 times. So how many different ways? What is the number of different permutation? Right? We have 3 different letters, right? A, E, B. or let's say A, B, E, certain order, or just say A, B, C, so we can understand it easily. So we have A, B, C, but each letter is repeated 4 times. Now the question is, how many different permutations are there? So because each one is repeating 4 times, so we have to have factorial. The total number of letters is 4 plus 4 plus 4 is 12. But factorial 12 divided by factorial 4 divided by factorial 4 times factorial 4, and so on. Because we have all three letters are uh, repeated 4 times. They're identical, right? So it has to be divided by, so factorial 12 divided by factorial 4 times factorial 4 times factorial 4. Okay, so this is an example again. When designing surveys, policers sometimes repeat a question to see if a subject is thoughtlessly providing answers just to finish quickly. For one particular survey of 10 questions, 2 of the questions are identical to each other, and 3 of the questions are also identical to each other. For this survey, how many different arrangements are possible? So with the 10 questions, 2 of the questions are identical to each other. 2 questions are almost the same. 3 of the questions are also identical to each other. So how many different arrangements are possible? Is it practical to survey enough subjects so that every different possible arrangement is used? So we have 10 questions with two that are identical to each other and 3 other that are also identical to each other. And we want the number of permutation. Using the rule for permutation, which with some items identical to others, we get, so you see here, 2 identical, 3 identical, so factorial 10 divided by factorial 2 times factorial 3. So this here, you cannot just say factorial 2 times factorial 3. You can just say, okay, the number is 6. No, it's not just, so you can see here, factorial 2 is 2, because 2 times 1 is 2. Factorial 3, 3 times 2 times 1, which is 6. So 2 times 6, 2 times 6 is 12. Factorial 10 is this amount, and you just divide by 12. 3,628,800 divided by 12. You get the 302,400. There are 302,400 different possible arrangements of the 10 questions, right? So you have 10 questions, but there are more than 300,000 ways of ranges of 10 questions, right? It is not practical to accommodate every possible permutation. For typical surveys, the number of responders is somewhere around 1,000, right? So it's not practical. One n different combination rule. So now we talk about permutation. NPR is factorial n divided by n minus r factorial. Combinations is almost the same. The only difference is the r factorial here. You see, n factorial divided by n minus r factorial is permutation. Now we have to divide it by r factorial again. So that's why the number of combinations is always smaller than the number of permutation if you are dealing with the same items and selecting the same number of items at the time. So the combination is much less. For instance, ABC, combination of ABC is 1. For permutation of ABC is 6. You see, permutation is higher than combination. So when n different items are available, but only r of them are selected without replacement, the number of different combinations, or it does not matter, is found as this. NCR equals n factorial over n minus r factorial times r factorial. In California's Fantasy 5 lottery game, winning the jackpot requires that you select 5 different numbers from 1 to 39. And the same numbers must be drawn in the lottery. So 5 numbers, the same 5 numbers. There is no order here. The winning number can be drawn in any order. So it's any order, which means the order does not matter. So order does not make a difference. The question is, how many different lottery tickets are possible, right? How many tickets are possible? That's why it is hard to win lotteries. So you are selecting 5 numbers from between 1 and 39. So 5 numbers could be 1, 2, 3, 4, 5, which is almost impossible. Or it could be 2, 3, 1, 5, or 1, 6, 7, 8, 9, and so on. 5 numbers. So now question be, find the probability of winning the jackpot when 1 ticket is purchased. So there are n different number possible. Different possible. There are n equal 39 different numbers available. And we must select r equals 5 of them without replacement, because the selected number must be different. Because array does not count, we need to find the number of different possible combinations. We get factorial, again, ncr equals factorial n over n minus r factorial times r factorial. N factorial is 39, so n is 39, so we have 39 factorial over 39 minus r is 5 factorial times 5 factorial. Again, you can also say, okay, I'm gonna subtract this 34 times 5 to get 5. No, you cannot just multiply the numbers and keep the factor on one side. No, you cannot do that. So you can see here 39 times minus 5 is 34, and we have factorial 5. So there are different ways you can do this. Easier way maybe can be to find what is factorial 39. If you have a scientific calculator, it might be just you enter the number 39 and then you press factorial, and then you write that down, and then you come to the bottom, you press the number factorial 34 again, you write the result, and then you find what is factorial 5, you write the result, and then you multiply those two results here at the bottom. After that, you divide the top by the result. But if you have a TI-84 plus or TI-84 plus, you can do everything in one time. But for that case, you have to use, once you do factorial 39, you have to use press division sign and open parentheses, and you do factorial 34 and then time factorial 5. Right? So there are different ways to do this, or you can do the simplification method. So factorial 39 is 39 times 38 times 37 times 36 times 35. Then the next one will be factorial 34. So you stop at factorial 34, so you can cross out this 34 and 34. Right? So all you have to do on top will be 39 times 38 times 37 times 36 times 35. And then factorial 5 is 5 times 4 times 3 times 2. Right? 5 times 4 is 20 times 3 is 160 times 2 is 120. So the result on top divided by 120 will give you this. If you select 5 numbers combination, so you're picking one 5 number. So 1 out of 575 times 755. 1 divided by 575,755. So see, this is even much better because the number, only you pick 5 numbers, but most already have order. The order matters. So the number will not be 575,757. It's going to be million, 10 million, because that is a permutation. First place, second place, and so on. Right? To win the big prize, must be some order. Otherwise, almost a lot of people will win the 5 numbers because the order does not matter. There will be more than one winner. But if the order matters, if the order does not matter, it's easy to win. But if the order matters, it's very hard to win the ticket, the lottery.